Hello and welcome to another bonus video from the DevOps Directive Docker course. In this video, we're going to be taking the sample application that we built throughout the course and deploying it onto Kubernetes. So we've already containerized it, and now we're going to define the necessary configuration files to deploy this to Kubernetes, which has become one of the most popular deployment targets for container-based workloads over the last 5 or so years. If you haven't already, you'll want to go to the GitHub repo DevOps Directive Docker course under my username Sid Palace, and either clone it or fork it, so you'll be able to work with the code base. You'll see in the deploying container section, all of the code that I'm writing for this Kubernetes module is located in this subdirectory. Now, the first thing that I'm going to do is to create a Kubernetes cluster. You could deploy your own onto virtual machines or bare metal system. I'm going to go with a managed cloud provider like Civo, just because they handle a lot of the operational complexity of dealing with the system components so that I can focus on the application components. I have this cluster already set up, but I'll create a new one just for the demo. We'll call it Docker course demo. We'll create it with 3 nodes. Choose the small size for each of those nodes. This will cost me $30 a month to run. I'm going to leave it within the default network in my account. I could also create a custom network if I wanted to isolate this from other projects. I'm going to create a new firewall here, and I'm going to allow traffic on port 80 because that's where the web traffic is going to come in. Port 6443 is where the Kubernetes API listens. I want to configure it so I can connect from my local system to talk to that Kubernetes API. If I wanted to lock it down further, I could lock it down to only allowing that traffic on my current IP address, but I'm going to leave it so that I can access it from any system as long as I have the proper credentials. And so by default, Civo installs traffic, which is an Ingress controller, and they set it up to use a node port. I'm going to turn that off and install it myself using a Helm chart. That'll just make it more standard if you're using a different cloud provider to be able to follow along with this demo. And then they also include the metric server, which I'll leave on. This application is located under the architecture tab here at the bottom. So I'll click it and that should turn it off. And so now we see only the metric servers being installed. And then I'll just click create cluster. One thing that's nice about Civo is that they have one of the fastest cluster creation times of any managed cluster. And so it should only take a minute or two before I have a working cluster. I've also installed the Civo command line, and I can use that to get the necessary credentials so that I can use kube control and Helm to talk to that cluster remotely. I've already authenticated, so I'll run Civo Kubernetes. And then ls. And we can see here is the cluster that we already had active, and this is the one that's being currently built. To get the entry for my kube config file to authenticate to this cluster, I can use the config option. So I'll do Civo Kubernetes config, get the name of the cluster, and then I'll use the --save command to incorporate this into my existing kubeconfig file, the --merge option, so that it doesn't overwrite the existing entries in my file. Okay, so it merged the kubeconfig file for this new cluster with my existing one. So I can run kubectx, which is a plugin for kubectl, and I'll switch over to Docker course demo. And we can see we have 3 nodes and they're all ready. Great. If I go back to the interface here, we can see that the cluster is running and we're ready to go. If you wanted to get that kubeconfig file from the UI, you could click download and then point your kubectl interface to it. But I've already done that with the CLI. And so now we can start writing our Kubernetes manifest for our application. We're going to have to write one of these for each of our services. But before that, I'm going to go ahead and use Helm, which is kind of like a package manager for Kubernetes-based applications, to install traffic. So that's that Ingress controller that's going to help us configure how to route traffic from the internet into our applications. And then 2, Postgres. So rather than writing a Postgres configuration from scratch, I'm going to use one from an organization called Bitnami, which will make it much easier for me to spin up an instance of Postgres on my cluster Unless you really know what you're doing, you probably would want to run your database outside of your cluster using some managed service. Civo has one. Most cloud providers have a managed service for databases as well. For the sake of simplicity and keeping everything self-contained, I'm going to deploy it into Kubernetes. The other thing that I'll point out that I've done ahead of time is I created this make target, which I used for the Docker Swarm example, where I'm building and pushing a specific copy of my container images, one for each service. I have these different Docker files showing a progression from very naive to production ready. And so this is specifically pushing number 5, 9, and 8 for my 3 services. And these are the versions that I'm going to use within my Kubernetes manifests. And these are all pushed onto Docker Hub into public repos. I'll create a new makefile in the Kubernetes subdirectory. And within this makefile, I'm going to create a couple of make targets to install traffic and install Postgres. The first one's going to be to deploy traffic. And I'm doing 2 things within this command. The first one is adding the Helm repo. So if I run this command now, and again, I'm pointing at the Docker course demo cluster. Let me first do a kubectl get pods -a. This will show me all the pods in all the namespaces. As you can see, we just have a handful of system pods. We're going to install traffic, and we're going to do so in the traffic namespace. So we're going to create a new namespace called traffic. We're going to install that Ingress controller into it. We're going to call the name of the release for this traffic, and we're using the traffic/traffic Helm repo. So it's a little confusing there, but this command will download that public repo and use it to install this into our cluster. So I can do make deploy traffic. We got an error here about the repository name. That's just because on my local system, I've already run that Helm repo add command. If this was the first time running it, you wouldn't get that error. Here, it created that release, and we should be able to see kubectl get namespaces. And now we have a new namespace created 21 seconds ago. And if I look at the pods in that namespace, and I have k alias to kubectl, so whenever I type k, just think kubectl. Traffic. We've got 1 pod running there, and it seems to be healthy. Great. Now, let's do the same thing for Postgres. I'll have a make target here, where again, I'm adding this custom Helm repo to my local Helm repo set. And then I'm going to use that repo to install my database. And I'm using this Helm upgrade -- install command because it allows me to run it over and over, both for an install or an upgrade. And so that syntax allows me to have the single command that I can rerun with no issues. I'm also passing a value here of my Postgres password. And so with Helm charts, you can specify a values.yaml file that you pass in. You can also pass in values at runtime. And so in this case, I'm setting this at runtime. Generally, you would have this in some external secret store. And wherever you're deploying this from, you would pull that and probably set it as an environment variable and pass it in this fashion so that you wouldn't have to have this credential stored in your version control system. So I'll do make deploy Postgres. And that's going to do a few things. Let's take a look at what was created. Okay, get pods. I installed it into the default namespace, which is why I didn't have to append a -n there. And we see this 1 pod is pending. Let's do a describe. We see that it set up a persistent volume claim. So like the volumes we're using in Docker, with Kubernetes, again, by default, your data will not be persisted. It is ephemeral. However, there is this concept of a persistent volume. And in this case, this will be backed by a persistent disk on Civo, where you can store data. And so we'll mount this in specifically into our container at the right path, such that data will get stored to that disk rather than just in the container that Kubernetes is managing, so that if we need to restart or move to a new node, those data will be persisted. We can now see that the database is running. It took a little while to provision because of that persistent volume behind the scenes. So I'll do k get pvc, or just pv. We've got this persistent volume, and then k get pvc. shows us the persistent volume claim from our pod, claiming that persistent volume using the Civo volume storage class, which was the default for our cluster. So I could even go here in the interface and see a volume that was provisioned by my Postgres instance. We can see it created this 8 GB disk to use for that Postgres pod. I'm assuming that you have some familiarity with Kubernetes, so I'm not going to describe the Kubernetes system architecture or anything like that. I'm going to dive right in and start working with the system and explain the different resources that we're creating and try to talk about why we're doing so. So now we've got traffic, which is our Ingress controller, as well as Postgres installed into our cluster. We can start writing the manifest for our applications. I'm going to add one more make target here, and that's just going to be to deploy our custom manifests. And I'm just going to call it deploy app. And this is going to run the kubectl apply-f in the current directory. So any Kubernetes manifest that I put into this directory will get applied here. I'll create a new file. We'll call it API golang.yaml. And then within this, we're going to define a couple of things. We're going to define a deployment. And so a deployment manages one or more replicas of the pod that we define. And the pod is going to have our Golang application image as the image, and then all the necessary config accordingly. We're also going to then define a service, and a service is Kubernetes mechanism for routing traffic to pods. And so we'll define a service that aligns with that deployment so that traffic will be routed to the service and in turn to the pods within the deployment. We can start by telling it that we want a kind deployment, which lives within this apps v1 API version. We're going to name it API Golang, and it's going to have this label, which will be used to align the pods to this deployment and eventually to route traffic to it from the service. At this point, we can define our spec. Our spec is where we define all of the attributes of the deployment itself. We can specify a number of replicas. Here we'll specify one. We want to have a selector, and a selector is how you tell the deployment which pods it's actually managing. The type of selectors that we're going to use is match labels. And the labels that we want to match are app, API Golang. And we're going to have this same label at the pod level, and that's how this deployment is going to know which pods it's managing. We can then write a template for the pod itself, and this is where we'll put that metadata for the selector to work on. So it will be metadata, labels, app, API Golang. And then within this template, we can actually have a spec for the pod. So whereas this spec at the top is the spec for the deployment, now we're writing out the specification for each pod that it is managing. And so while that top level spec is the specification for the deployment, this lower level spec is the specification for the pods that the deployment is managing. And so within here, we're going to tell it which containers exist. And so we need a name for that container. I can call it API Golang, and we'll give it an image that it's going to use. And in this case, it's that same image that I built and pushed to Docker Hub. And that should now be sufficient for us to deploy it. So let's try to deploy it and see what happens. It's going to crash because we're not specifying the database URL or passing it that information. But we can at least apply the deployment and see Kubernetes trying to create and recreate this pod. So I'll do k make deploy app. Now if I do k get pods, we can see in addition to our database pod, we also now have this Golang pod, and it's getting an error. So let's look at what that error is. I can do k describe pod. It successfully got the image, started the container, and then crashed. And so let's look at the logs from that pod with k logs and then the name of the pod. Here, it's trying to open the file containing the database URL that doesn't exist. In this case, I'm just going to temporarily set this as an environment variable. And the way that I can do that, under the containers here, I'm going to have the env key, and then we'll have a name, and this will be database URL. And then the value that we're going to use is going to be this, which refers to the Postgres database that we installed using Bitnami. The way that we know that is if I do k get service, this service was set up by the Helm chart, and it is pointing to the Postgres pod. I'm using that as my host name. I'm listening on port 5432 and using my username and password here. Let me now reapply the Golang API deployment. And now it's no longer crashing because it was able to boot up and connect to that database successfully. Let me port forward to this pod just to make sure things are running, and then we'll continue to update this config, removing the sensitive data, adding additional config parameters that we care about until we're happy with the result. But in the meantime, I can do k port forward name of pod, and then I know that it's listening on 8080. And so if I now go to localhost 8080, we can see we have my Golang API running in a pod in Kubernetes, hitting that database and returning the result. However, we would never want to just pass this in as an environment variable. Instead, we want to use the Kubernetes secret feature and read it in that way. And so what I'm going to do is actually create a new file called secret.yaml. It's going to be the API version v1 and of kind secret. There is a type, and it's opaque. And then we'll pass it the metadata, and the name will be database URL. And then there's a few ways you can get this data in there. The easiest is to use the string data field, where we have a key. So in this case, database URL. And the value is going to be that value that I had before that refers to the connection string for the database. And just as a reminder, you wouldn't normally store this in plain text in your version control system. You'd want to create this secret in another way. You could create it ahead of time manually, but that's not best practice. You can use a system like sealed secrets, where you have this encrypted in your version control system and it will automatically create the secret in your cluster. Or you could have this managed within your CI/CD pipeline such that it's automatically created that way. Let me apply that. Now I have this database URL secret that I just created. If I wanted to get the value of that, I can do get secrets database URL in the format YAML. When we created it, it actually base64 encodes this value. And so if I wanted to get that out, I could pass that to YQ, which is a tool for interacting with YAML. I can do .data.database URL. So that just gave me that base64 encoded string, and then I could decode it by piping it to base64-d. And so we get out the database URL password that we put in. And so this is now stored in the cluster in that secret. And I can now reference that from my deployment. So I'm no longer going to need this environment variable here. I will have the environment variable port just to make it clear to end users that that is the port it's listening on. So that's 8080. And now instead of env, I can use env from and reference that secret. So this will be a secret ref, and this will be name database URL. We'll also, while I'm at it, notice that there's these squigglies. I have the Kubernetes VS Code plugin installed, and it is warning me. And I believe the reason for these squiggles is that it doesn't like the fact that I don't have a resource limit set for my containers, such that one container could take all of the resources available and starve out the others. And so let's add in those resource constraints. And so the way that we do that is at the container level, we have resources. We can set limits. So this will be the maximum allowable resources that the container can use. And I'll set the memory limit at 100 megabytes. We can also set requests, and this will be the minimum Kubernetes will enforce to have available at runtime for this container. And so again, I'll do memory. I'll set this equal to 100 megabytes. And so in this case, we're saying, give me at least 100 megabytes, but don't allow me to go over that. Then I'll also set a CPU request of 50 millicores. So that is 5% of a CPU core for this particular container. I can iteratively continue to apply my configuration. And I see that I have made an issue here. So it doesn't like on line 32 how I'm mapping. Oh, I have an additional colon here. Let me save, apply. The nice thing about Kubernetes is that every time I update this configuration, it automatically deletes the old pod and creates a new one very, very quickly. And so here I can see 3 seconds previously, I updated the config, Kubernetes stopped the old container, removed it, added a new one within this new pod. The other thing that we'll want to do, similar to how we did in Docker Swarm, is add a health check to tell Kubernetes when my application is ready or listening. And in this case, I'll use the readiness probe key, and it'll be just an HTTP get command. So I'm going to issue a get command to my container, and the path for that will just be /ping, and the port is going to be 8080. And so one interesting thing here is that these health checks are managed by the Kubernetes system versus in Docker Swarm, the health check was executed internal to the container. So we needed to have, for example, we wrote and built a health check binary into our container image so that we could call that from within the container itself. There's also a couple of security features that we can take advantage of here. The first one being the security context. And so the security context, we can tell Kubernetes that we do not want to allow privilege escalation. We also can explicitly say that privileged is false. So we're not giving privilege and we're not allowing escalation. So that should help lock things down. And then pod level, rather than the container level, we can set a security context with a setcomp profile and of type runtime default. Let's make sure I don't have any typos. Reapplied, great. And so now I have a deployment. Let me just show you what happens if I do this. I can change the number of replicas to 5, apply that, get pods, and we see we now have 5 copies of my Golang application spinning up. If I do get pods -o wide, and then minimize this, we can see that they're actually running on different nodes. So this is the node name. I created 3 nodes in my cluster. In this case, I can have copies of my application running across different nodes, which enables me to have higher availability in case one of these nodes were to be unhealthy or have a networking issue. Traffic can get routed to those other copies. I'll change this back down to 3. Previously, I port forwarded directly to a pod. However, if we want to route traffic and have that load balanced across all of those 3 pods, we need to use what's called a service. Generally, you would define this in a separate file. Maybe I'd call it API Golang service. But for now, I'm just going to include it here at the top. It is the service kind within the V1 API. We need to define the name for it, which will be under the metadata field. In this case, I can just keep calling it API Golang. And then we need to define the specification for it. The most important thing here is the selector. And so this is how you tell the service which pods it should route traffic to, just like how the deployment has a selector to tell it which pods it's managing. And in this case, we're using that same label. So in this case, we'll have app API Golang. That will tell it route traffic to any healthy pods with this label applied to them. In this case, we will define the ports for the service. We'll specify the port is 8080. The target port is also 8080. So traffic coming in on 8080 is routed to 8080 in the container. And the protocol is TCP. We'll do make deploy app. Now if we do get service, we can see we have this new API Golang service. Let me describe it. And it has 3 endpoints because we have those 3 pods for the API Golang deployment. So that tells me that the selector is properly set up. It's detecting the backends that it wants to route traffic to, and we have those internal IP addresses within the cluster that it's going to route to. And so that's pretty good in terms of the configuration that we have for the Golang API. Let's copy this and make the modifications that we need to have our Node API as well. So I'll just copy and paste. I'll do a find and replace for API Golang. Turn that to API Node. Replace all. We know that the Node application is listening on port 3000 instead of 8080. We had this port defined as well as an environment variable. We still need to load in that database URL secret. We'll give it the same resource limits. We need to update the image. And so in this case, doing that find and replace did so. However, for Node, we're using version 9 as the one that I built and pushed. Version 9 is the one that I built and pushed, so that will need to be version 9 there. But otherwise, I think everything else should be good. We have the same path for the readiness probe. And let's just go ahead and apply that. Make deploy app. Okay, get pods. And you'll see we now have 3 Golang pods. We also have 3 Node pods because we left that replicas equals 3. And this is interesting. We see the pods are running, but they are not ready yet because it's using that readiness probe to check whether or not my application is accepting traffic. And so it's taking a little while to boot up. Let's actually look at the logs from one of these and see what's going on. So I'll do k logs name of pod. It says example app listening on 3000. Let's port forward to 1 and see if we get the proper response. I need a dash there. Okay, so the Node API seems like it's working. Why are we getting that ready? So it thinks that our pods are not ready. Oh, it's because my readiness probe specifies a port. So it was trying to ping Node on port 8080 when it's only listening on port 3000. And so if I change this to 3000 and reapply, okay, get pods. You see it's deleting the old ones, terminating them, and bringing up the new ones. And now for the new Node API pods, it is stating that they're ready because we have our readiness probe set up properly. So now we've got 3 copies of our Node-based API running, 3 copies of our API Golang container running. Now let's move on to the front end. And so once again, we're going to have a very similar configuration. I'm going to copy over this, rename it to client React Nginx. We're going to find and replace from API Node to client React Nginx. Here we're going to listen, because it's that unprivileged Nginx image, we're going to listen and forward to 8080 because that's what it's bound to. I believe, let me just look at what my image is named. So under 6, client React, makefile, Sid Palace. Okay, so this is the image name, and we are using image number 5. Cool. So that looks, does that look right? Client React Nginx. It will be number 5. We don't need this port. We don't need this secret because the front end doesn't connect to the database directly. We could modify our resource limits if we wanted, if we had something specifically. I do have within my Nginx config a health check route at the path ping. However, it's listening on 8080. That all looks good. However, now that I'm using Kubernetes and I have that Ingress controller, instead of routing traffic to my Nginx front end and then proxying it to my APIs, I'm going to use the Ingress controller to route traffic directly to my APIs when we hit the /API/Golang or /API/Node paths. And so I do need to modify my Nginx configuration slightly to accommodate that. The way that I'm actually going to do that is to create a config map. And so this is a way to store arbitrary key value pairs within Kubernetes. I'm going to create a config map containing that updated Nginx configuration and then mount that into my pod at runtime. And so similar to the service, normally this would be a separate file. I'm just going to bundle it in here for the sake of simplicity, but we're going to define what is known as a config map. So it's in the version 1 API of kind config map. We need to define the metadata, the name. This will be Nginx conf. The data for this is going to have a key, and that key will be the name of the file that I'm going to mount it in as. So in this case, it's default.conf. And then this syntax just allows me to have a multi-line value here. And so I've got the value, let me just copy it in. It's a more simple Nginx config because I no longer need to have the proxy set up. So I'm just defining it, telling it to listen on 8080. I'm giving it this as my health check. So it's going to listen on ping and return 200 pong if you hit /ping. And then for everything else, it's going to serve the built React client files from that well-known location. Those are built into the image at that path. Now to get this config map into my container so that it uses this rather than the default that was built in my container definition here, I'm going to add a volume mount. So I'm going to specify, first I'm going to specify a volume. So I'll define a volume here at the pod level. So you define which volumes you have at the pod level. And in this case, it's going to be config map. And that config map will be the one that I defined before. That is the name of Nginx conf that I just defined below. And the volume name will be Nginx conf. And so with the volume now defined in the pod within my specific container, I can tell it to mount that at the proper path. I can specify the volume mounts, the mount path, and this will be the location in the Nginx container that it's expecting to find that configuration. And the name of the volume that I want to mount there is Nginx conf. And so I'm creating the volume here, referencing it here, and mounting it at that path. It will contain the contents of this file, which will override the default conf that I've built into my image to begin with. And so let me now apply that. What did I mess up here? Oh, this should be plural, volumes. All right, there we go. And so to make sure that this volume was properly applied, I'm actually going to do get pods. So now I've got these 3 Nginx pods running. I'll exec into one of them. Now I have a shell inside that pod, and I'll take a look at cd etc, cd nginx, cd conf.d, cat default.conf. We see this is the more simple Nginx conf that I included for my config map, rather than the one that I have in my code base, which has some additional proxy configuration that we used with Docker Compose or Docker Swarm. So that is now doing what we want. And let me port forward to that service, port forward service 8080. And now I should be able to load this on 8080 and see my front end. Okay, so here we go. I'm loading my application. However, it's unable to talk to my 2 APIs. And now the reason for this is that I haven't set up Ingress, so it's trying to hit /API/node or /API/Golang, but it doesn't know, there's no way for it to actually load those APIs because I haven't configured the ingress yet. And so the final thing that I need to define is what is known as an ingress route. And so because there's some additional features that each ingress controller uses that are not supported by the ingress resource, you end up potentially having custom resource definitions. In this case, rather than using ingress, I'm using ingress route, which is a traffic specific construct. There's a new API in the works called API Gateway that is meant to replace the ingress resource. And so eventually you would be using that API Gateway. In this case, I'm using a traffic specific CRD, custom resource definition, that will allow me to have all the different features I need, such as path rewriting. And so I'm going to create a file here called ingress route.yaml. And so this is a specific resource that is not included by Kubernetes by default, but was installed when we installed that traffic Helm chart. So a default cluster wouldn't have this, but once you've installed traffic with the CRDs, you'll now have access to this new kind under this API version. As you can see, it's namespace to the traffic v1 alpha 1 namespace. We need to define the metadata for it. In this case, it's just going to be the name. I'm going to have this be just the primary ingress route. And then we need a spec for it. And the spec is where we define everything that we want to have happen with this ingress. I can define one or more entry points. In this case, I'm just going to call it web because this is traffic coming from the internet, from the web. And then I'll define one or more routes that my ingress route is supposed to utilize. And so I'll have one rule where I'm going to tell it what to match on. So inbound traffic matching a particular host. And so in this case, I'll have host, and this will be my public DNS settings that I want to match for. And so here, my host is going to be Docker course Kubernetes /.devopsdirective.com. So I'm having this subdomain is going to route traffic to my cluster. I'll set that up on Cloudflare, where I manage my DNS. And then the services that this route is going to have, we'll have of kind service. It'll have a name. The front end service will point to our front end. So client React Nginx will point to our client React Nginx service. It's in the default namespace. It's on port 8080. And it is using HTTP as the scheme. We'll now set up rules for each of our additional API endpoints, so it'll be quite similar. So I'll copy it down here. In this case, we want the host to still be the same. However, we're going to add a path prefix here. And that path prefix is going to be for each of our different APIs. So if you remember, our application is listening here on API node on 3000. And then if we hit the API Golang path prefix, we will want to route it to the Golang API on port 8080. The other thing that we need to add to these rules is that we need to strip the prefix. So in this case, it's going to come in with that /API/node on our, that's the path that we're hitting. However, the Node and Golang applications don't expect requests to come in with that additional prefix, and so we need to strip that out. There's a middleware that traffic has integrated that we can use to handle that. So I'll add another key here that just says use that strip API prefix as middleware for both this API node rule as well as my API Golang rule. And then I need to define what that middleware is as another Kubernetes resource. And so that again is a custom resource defined by traffic called middleware. We'll call it metadata. We need to add the name so that we can reference it up above like we did. This will be strip API prefixes. And then the spec for this will be strip prefix force slash false. So that's just whether or not it wants to always enforce that there's a slash on that prefix or not. And then the two prefixes that we care about are API node and API Golang. So let me deploy that. Unknown field route. Again, this should have been plural. And this should have lived under the strip prefix key. Okay, so we now have our ingress route defined. And now I need to set up Cloudflare to point traffic to this new cluster. And so when I set up traffic in the cluster, it automatically provisioned this load balancer. And so let me just do this. I'll do k get service in the traffic namespace. And we can see it provisioned this load balancer, and it has this public external IP. And so that's the external IP that I'm going to route traffic from Cloudflare to. So let me just log in here. Now under DevOpsDirective.com, under DNS, I'll edit this. This was the previous cluster. I'll now update it to be the new cluster. Save. And so now if I go to docker course kubernetes.devopsdirective.com and load it, it's going to route traffic to that new cluster. However, it looks like my services are still not quite working right. And taking a look at the ingress route definition, I think it's because this path prefix needs a leading slash that I didn't have there. And so it was not detecting those paths as being associated with these rules. So let me reapply that definition. Everything's unchanged except for my ingress route. And now if I go back here and I load, I get data from my APIs returned to the front end. If I load one of these directly, /node, we get our node API response. And if I do Golang, I get my Golang response. And so now it appears that everything is working as expected. And so when I load this page in my browser, that makes a request, which looks up the DNS, looks up my Docker course Kubernetes DNS record, which gives the external IP address for my load balancer in the cluster. So that traffic is routed there. That load balancer then is tied to my ingress controller, that traffic installation, which is using my ingress routes to determine what to do with the traffic. So on this route path, it gets forwarded to my Nginx front end. When we have the API node or Golang path prefixes, that traffic gets routed directly to those APIs. And so now I have all of these services running in my cluster. I've got my database that was installed via Helm using that Bitnami Helm chart with a persistent volume backed by a persistent disk where those data get stored. I've got 3 copies of my Golang app. I've got 3 copies of my Node app. I've got 3 copies of my front end. And we can very easily, using Kubernetes, scale up and down. And that's the beauty here, is that I can deploy a new version and I can specify exactly how I want that to roll out. I can terminate one replica at a time while I roll out the new versions. I've got my services defined to route traffic and load balance, internally load balance across my different pods. And I used that config map to load in a custom Nginx configuration at runtime that was different from that was built into the image. Hopefully that gives you a sense of the path required to take a containerized application and bundle it up into the necessary Kubernetes manifests so that we can deploy onto Kubernetes. We defined pods for each of our services, wrap those in deployments, which allows Kubernetes to automatically manage those pods. We then put services in front of them, and had an external load balancer using traffic as our ingress controller to configure how specific requests should be routed to our different services. The beauty of using an orchestrator like this is that is all handled across 3 different nodes, and our workloads are distributed nicely across those. There's even options to tell Kubernetes specifically how you want to distribute your workloads. If there's considerations about, oh, we want this workload to always be co-located with that workload on the same node for networking latency purposes, or we want these pods to be always located on different nodes within the cluster, etc., etc. I hope that you'll be able to take the lessons shown in building out these deployment manifests and apply them to your applications as you move to deploying them to Kubernetes. That's it for today. Remember, just keep building.